All right. And the next case, there are two more cases your textbook talk about. But in general, there's solving OD, there can be many different type, more specific type. So if you are doing research and you need to solve a differential equation, which doesn't look too difficult, if too difficult, you probably will just do it numerically. If you want to solve it, see if there's a closed form, then if it doesn't fit all these simple form, then one last step you can check is find a more comprehensive math handbook and look up this ODE thing. And there will be more different type of ODE, and try to match your equation with that and see that they give you a analytic solution. Okay, but if everything fails, obviously you go back to numerical, which is fine. Nowadays, numerical solutions are quite easy for ODE. I mean, it depends on the form of the equation, obviously. Right. Now the next step is so-called homogeneous. This homogeneous is saying that all the different terms in the equation have the same property. It's not whether the equation is only proportional to the y, no extra term. That kind of homogeneous is a little different in terms of the meaning. So, so for this one, first is P. Then go back to the standard form. Y, x, y, dy. So this is actually the special case of the next case. Both cases are similar, actually. You just obviously both P and Q can be complicated functions. So P and Q both may have more than one terms, but so finally it may not have just two terms. It may have more than two terms, and for each term you give x as if you count the power of x and power of y, if they are the same, then it's called homogeneous, right? And then you can do a transformation to make it separable, right? And the transformation is y is xv, right? And obviously this is for just power. The coefficients are all power of x and y. If this is a more complicated function like sine x or exponential x or y, then obviously this would not work, right? Because you are counting the power of x and y, right? And so it's a special case, but I mean, for some simple situation that give you the analytic solution that in a systematic way. There's no general discussion except just look at example. So there's an example in your textbook as 2x plus y dy dx plus x dy 0. So it satisfies the homogeneous condition. So the power of each term, so this is power 1 and 1 and 1, so 2. This is also power 1. And the other term is actually power 1 and 1 to the power of 2. So all terms has power of 2, right? So so it's homogeneous, and you can use this transformation. Okay, so what you do is so originally it's a function of x and y, but with this transformation, you want to do it transform it to a function of x and v, right? And so that's what you do. 2x, y is x plus v. x times v dx, right? And then x. Now dy is just using this formula. I mean, this transformation becomes v dx is x dv, right? Let's group all the terms. What you see is you have 2x, and then add this to the others, you 2x v, right? And but you have the 2x factor, so 2x 1 plus v dx plus x squared dv is 0. But now that's this is separable now, because you can divide the x to the other side. So you have, or divide 1 over v to the other, x to the other side. So you have 2 dx over x plus dv over 1 plus v is 0, right? And now this is separable, then you can solve for it directly by integral 2 log x plus log 1 plus v equals to a constant, whatever equals to a constant. I mean, you can set the constant later. Then you can solve for that by taking the exponential function and combine the two, becomes x times 1 over x squared times 1 over so x squared 1 plus v log of that, right? Log of that equals to exponential of this, but it's still a constant, so you can say it's just this is another constant, right? So let's solve for that. Because usually you want the x and y out. You want y as a function of x, so this is equals to x squared plus x times y. Right. And you solve for y, so y is a constant minus x squared divided by x, or c over x minus x. Right? Is it? Did I do it correctly? Right. Okay. All right. Finally, you check again. You check that. So for this one, there's no initial condition, right? Is your textbook solve initial condition? No. I mean, then the initial condition will fix the constant c. Right? If you x sub 0 or this x sub 0, that's set is y sub 0. Then you can solve for your constant c. But now you go back to the original equation, which is this one, right? Oh, dx, or the way the one that wait. I mean this is just dy dx equals to 2x plus y over x minus 7, right? So equals to minus 2 minus 1 over x, right? So x divided by x. Right. So the original differential equation is this one. Right. You want to check whether that is the case. So by using this, and you check that dy dx is just minus c over x squared minus 1. And now you can check 2 ways. Or one, you can just substitute this solution to this terms and see if you get the same thing. That this equals to minus 2 minus p over x squared minus 1. Right, that's y over x. Y is this one divided by x is this one. So that is equals to minus 1 minus c over x squared. So that's correct. Okay, so that's the final step. You check whether your equation is valid, satisfied the original, the solution satisfies the original equation. Okay, so
we still use the previous methodology, the power.
this one.
Or no, I mean this example. We'll have to use the previous method that we did using.
Well, you can check whether that is true. So that's a good question. So dy dx, right? So this is just this one. I just solve it. This one from this one. So this is your p. This is your q, right? Obviously, it's not separable at least at this stage. It's not separable. This is not the function of x purely. This is not the function of y, and no obvious rearrangement to make that the two terms are pure function of x or y. And now the second you check is, well, the partial p partial y is equal to the partial q partial x. Partial p partial y is this one, right? And partial q partial x is partial 1. So this actually turns out to be separable. And you can check whether that is not separable. That turns out to be exact, not separable, right? And now you can use the other method and try to see if you get the same answer. Probably will. So that is a good observation. But I mean, obviously this method will may solve for other cases. Well, that is not separable, but turns out this one is separable. Okay. All right. Now this is just the special case of the next case. The next case is slightly more general. It's kind of homogeneous in the same sense, but then you're just taking the x power and y power differently. And so this is so-called isobaric ODE. You have x, this example, x squared minus y. X plus x dy minus 0. And now you can start to see this is p, this is q, right? Partial p partial y is minus 1, partial q partial x is 1. So this is now this is not separable. This is not exact, right? And it's also not separable, right? And but this one, the difference is that the power x and y you weighted differently. So if you weight x usually, so there's a power of 2, and then dx to the power of 3 totally, and y is you weight it differently. You weight y as a function y, the power times the factor m. So if you can choose m so that all terms have the same power after you weight it, then this is isobaric. Obviously, because the first term is 3, then you weight this as 2. Y has a weight of 2, so it's original factor of 1, but you multiply by 2, and then make it 3. And dy also have a factor of 2, so 2 and 1 is also 3. So this is isobaric. Then the transformation is y is x to the power m times v. Right? So that is what we choose. So this is so that becomes x squared v do this transformation. And now you do the same thing. So x squared minus y x squared v and x plus x. Now dy is this form. So you have 2x v dv dx and plus x squared dv. Okay. Now I can group the dx term. X squared v, you have two of them, and then minus 1. Altogether is x squared plus x squared v dx and plus x cubed of dv. Now this one again becomes a separable because you take x squared out, becomes 1 plus v, and divide that to the other side, or the other term. So this implied x squared out divided by x cubed, so dx over x plus dv 1 plus v equals 0. But this one is very similar to what we did before, right? So log x plus log 1 plus v equals the constant. And so 1 plus v times x also equals the constant. So 1 plus v equals some constant divided by x, right? And v is v is y over x squared. Y over x squared. Right. Then you can solve for y. So y is multiplied by x squared. So c times x minus x squared. Okay, so that's supposed to be right there. Yeah, correct. Right. So again, there's no initial condition for this example, right? So anyway, now you check whether you satisfy the same equation, right? The original equations as dy dx is y minus x squared over x. Right. Yeah. Now you check that for your solution dy dx, the left-hand side is c minus 2x. And the right-hand side is y is c x minus x squared, and then minus another x squared. Divided by x. And so with this x equals to c minus, and cancel the one factor minus. Okay. Right. Finally, we got it through. The textbook get the same answer. Y is cx. Yeah. Right. Okay. So it's okay up to here. So all these are just like that. And then obviously this is just a very limited cases. So, but if you found other formula for other cases, it's just going through the same thing. So plug in the formula or the algorithm how you solve it, and finally you come up with a solution. And remember the final steps: check your solution against the original equation. Okay.